Good day. We are going to present to you our special course project output, entitled Wastewater Management of Mining and Its Effect on Groundwater and Ecosystems, a Review. Introduction. This paper addresses the effects of wastewater management on the groundwater and ecosystems as anchored on the Republic Act or RA number 9745 titled An Act Providing for a Comprehensive Water Quality Management and for Other Purposes, also known as the Philippine Clean Water Act of 2004 and DENR Administrative Order or DAO 2000-08 or the Water Quality Guidelines and General Effluent Standards of 2016. Large-scale mining activities have major impact on the environment. Treatment of wastewater is crucial for mining applications. Water is critical to the mining industry because it is used in mineral processing to extract rich metals from ore. However, using water in this manner results in the accumulation of mineral pollutants and other solids in the process water supply. This results in tainted mining effluent that, without treatment, cannot be utilized or returned to the environment due to public health concerns and environmental regulations. As such, mining operations require a continuous and stable supply of clean water to operate effectively. Mine waste from abandoned mining sites can degrade the environment and create ecological imbalances in water bodies that receive it. Local communities are impacted by heavy metal pollution, which may pose health hazards to the general public. While both the public and private sectors have implemented numerous mitigation and remediation measures, the door for trials, feasibility studies, and enhancement is always open to address this topic. Water resource management based on science is critical for resolving water supply challenges. Recycling and reusing wastewater is widely recognized as a critical component in achieving sustainable water resource management. Natural purification of wastewater has a number of limitations, including the fact that it takes a long time, is significantly affected by climate change, and is inefficient. Thus, it is critical to create effective ways for treating and recovering wastewater. Research objectives. This study aims to determine the effects of wastewater management on the groundwater and ecosystems as anchored on the Republic Act or RA number 9275 titled An Act Providing for a Comprehensive Water Quality Management and for Other Purposes, also known as Philippine Clean Water Act of 2004 and DENR Administrative Order or DAO 2006-08 or the Water Quality Guidelines and General Effluent Standards of 2016. This research proposed the following: to examine wastewater management, especially in its ability to clean and protect water. This means that the water must be clean enough so that it can be domestically used by people and by industry for commercial purposes. It also must be clean enough to release into the groundwater like oceans, lakes, rivers after it has been used. This research will also investigate risk assessment in mining locations and the influence of mining on groundwater and ecosystems. The best management methods and risk assessment procedures have been established, particularly in locations with large quantities of mining effluent. Pollution of groundwater and subsequent contamination of humans is a significant issue. Statement of the problem. This study is all about the wastewater management of mining and its effects on groundwater and ecosystems. Specifically, it intends to answer the following questions. First, what are the different ways to address the problem of mining industry in terms of wastewater management? What are the different wastewater treatment technology? Why mine wastewater management is important during mining operation? What is water management in mining? Based on the results, what recommendation may be proposed? Significance of the study. The wastewater management is significant in the study of environmental and sustainable development under the water quality, accessibility and availability, as it introduces water remediation and mitigating measures. Hence, the researcher believes that this study can give significant contributions to the following. Mining industry. Mining industries in the Philippines are always having an advocacy to be responsible mining. Therefore, the study will greatly benefit them as it helps mining companies in their propaganda under the environmental protection and sustainability. Through wastewater management, water contamination will be lessened or eradicate, which also result in the mining bad impact in land and aquatic biological components. Mining communities. The success of this study will benefit any mining communities, especially those communities that suffer in this issue. The residents, farmers and fisher folks living near the vicinity of mining are also at ease in their livelihood in place because wastewater contaminants can possibly kill sources of livelihood such as fishes, crustaceans, birds, domesticated, wild animals and other agricultural products, and even in the ecosystem. Therefore, the impacts and effects of wastewater and groundwater like streams, ponds, rivers and farmlands will be lessening and eliminated. Environmentalists. In this study, the environmentalist will take their concerns and attention in this study as it helps in their responsibility and commitment to the call of environmental protection. Engineering students. This study can be their inspiration, basis, and reference to their chemistry class laboratory and other mining subjects. Also, it widens their knowledge in water quality, protection, and sustainability. And lastly, researchers. This study boosts the technical and engineering skills of the researchers and related fields in the profession, as it can be a guide or reference for the future correlated studies, and to be able to respond to the call of nature by providing a way to become a responsible mining and enhance the environmental protection and sustainability, especially in water quality, associated living species. Scope and limitations. The study will focus on the impact of wastewater towards groundwater and ecosystem only. The study will review available published literatures from 2005 to 2022. The study is only applicable to mining industry, specifically in the Mine Environmental Protection and Enhancement Department. Review of related literature. This chapter presents studies and literatures used to expound concepts and discussion regarding the importance of wastewater management in mining and its effect in the groundwater and ecosystem. Mining wastewater management and its effects on groundwater and ecosystems. According to Chelebi A. and Ozdemir S. 2014, mining activities on a large scale have a significant impact on the environment. It is critical to determine the magnitude of the effect and to monitor it. The purpose of this study was to examine risk assessment studies in mining areas and the influence of mining on groundwater and ecosystems. The best management methods and risk assessment procedures have been established, particularly in locations with large quantities of mining effluent. Pollution of groundwater and subsequent contamination of humans is a significant issue. Wastewater treatment and mineral processing of non-ferrous metal resources. According to Meng S. et al. 2022, water used by mining operations must be fully collected and repurposed to ensure clean production. This necessitates the treatment of mineral processing wastewater effectively. Wastewater generated during the processing of non-ferrous metal minerals contains a complex variety of contaminants in high quantities, complicating thorough treatment. The origins and risk associated with wastewater generated during non-ferrous mineral processing are discussed, as well as the methods for eliminating heavy metal ions and organic compounds. Heavy metal ions are frequently removed via chemical precipitation and adsorption techniques. Chemical precipitation techniques are classified as hydroxide and sulfide precipitation. The majority of organic compounds are eliminated via oxidation processes such as electrochemical oxidation, photocatalytic oxidation, and ultrasonic synergistic oxidation. The importance of advancing water quality monitoring in Andean. According to D. Garcia et al. 2019, researchers claim that human pressures and ecosystem dynamics in the Andes can be radically different from preconceived ideas, and that current knowledge of high mountain freshwater ecology is insufficient to assess mining impacts. Traditionally, water quality monitoring in mining contexts focuses on locations prone to receiving mining pollutants. Field and laboratory measurements are compared to well-defined quality standards for mining activities. Such an approach provides information for remedial responses. Example: pH or sediment control deemed as responsible mining since environmental laws are being complied with. However, such traditional water quality monitoring approach has not been conceived for the sustainability of freshwater ecosystems withstanding the multiple and complex impacts of mining. Development in water quality monitoring and management in large river catchments using the Danube River as an example. According to D. Chapman et al. 2016, effective management of water quality in large rivers requires information on the influence of activities within the catchment, urban or rural, throughout the whole river basin. However, Traditional water quality monitoring programs undertaken by individual agencies normally relate to specific objectives, such as meeting quality criteria for wastewater discharges, and fail to provide information on basin-scale impacts, especially in transboundary river basins. Ideally, monitoring in large international river basins should be harmonized to provide a basin-scale assessment of sources and impacts of human activities and the effectiveness of management actions. Advancing towards functional environmental flows for temperate floodplain rivers. According to UNDP, WEF, CCSI and SDSN, 2016, the abstraction, diversion, and storage of flow alter rivers worldwide. In this context, minimum flow regulations are applied to mitigate adverse impacts and to protect affected river reaches from environmental deterioration. Mostly, however, only selected and stream criteria are considered, neglecting the floodplain as an indispensable part of the fluvial ecosystem. Based on essential functions and processes of unimpaired temperate floodplain rivers, we identify fundamental principles to which we must adhere to determine truly ecologically relevant environmental flows. In addition, literature reveals that the natural flow regime and its seasonal components are primary drivers for functions and processes of abiotic and biotic elements such as morphology, water quality, floodplain, groundwater, riparian vegetation, fish, macroinvertebrates, and amphibians, thus preserving the integrity of floodplain river ecosystems. Breaking barriers for a bio-based economy. Interactive reflection on monitoring water quality. According to T. Metz, et al., 2017, in a transition to a bio-based economy, new ways of monitoring waste, streams and water quality can then contribute to sustainable production processes. As niche innovation, new ways of monitoring face systematic barriers. The present article examines how barriers to change manifest in discursive practices with differing normative attachments and implications. A frame analysis revealed to competing frames. First, the dominant norm water frame in which thresholds of chemical compounds are used to set policy targets. And second, the contesting living water frame, which entails innovative continuous monitoring tools that take into account the ecological effects of chemical compounds. In this, it introduced the concept of interactive reflectively as a discursive tool to collaboratively visualize, scrutinize, and overcome discursive barriers to innovations. The stakeholder dialogue shows how systematic barriers are uttered discursively in niches or other forms of responsible research and innovation, and many hinder change even at the niches level. Environmental Law Alliance Worldwide. According to a law, 2010, the most countries require an environmental impact assessment (EIA) before giving the green light to a mining project. EIA processes provide a valuable opportunity for citizens to participate in decisions about mines. The problem is, project proponents often submit long, complex EIA documents that are incomprehensible to lay people. A law has helped partners around the world evaluate dozens of EIAs for proposed mining projects. The guidebook consolidates what we have learned and points to many critical resources for communities seeking to make their voices heard about proposed mining projects. Biomonitoring and bioindicators used for river ecosystems. Definitions, approaches, and trends. According to L. Lee, et al., 2010, in this paper, it presents a review on concepts, current use, and anticipated future directions of biomonitoring approaches and bioindicators used for river ecosystems. Periphyton, benthic macroinvertebrates, and fish are the most common indicators in river biomonitoring, which can be used separately or contemporaneously. Their importances in the ecosystems and advantages for biomonitoring have been described in detail. Commonly used biomonitoring approaches include diversity, biotic indices, multimetric approaches, multivariate approaches, functional feeding groups, and multiple biological traits. Among these techniques, biotic indices and multimetric approaches are most frequently used to evaluate the environment health of streams and rivers. However, functional measures have been increasingly applied as a complementary approach to reflecting ecological integrity. Furthermore, recent research have demonstrated the efficiency of molecular techniques on enhancing the taxonomic resolutions and detecting the genetic diversity in river biomonitoring. Methodology. This chapter provides various methodologies that were used in gathering data and analysis which are relevant to the research. Under the methodology, we have what we called stages of water treatment. In line with this, we have preliminary treatment, which describe into two. First is the screening. Main objective of this treatment is to remove floating objects such as cloth, wood, plastic bags and other larger objects which include suspended matter. For this screening is carried out where wastewater is allowing to pass through screen made of iron bars with spacing of 1 to 2 inches. Spacing is narrow enough to hold back the floating objects. Second, skimming. Oil, grease and other impurities which are lighter than water rises to the surface and can be removed by mechanical skimming. Skimming tank's oil and grease trap is so designed that the lighter material like oil and grease remains on top of liquid. For effective removal, sometimes compressed air is sent through a diffuser plate located at the bottom of tank. Shows the main treatment steps for oil wastes and waste oil below. Primary treatment. It involves settling of colloidal and suspended matter as sludge. The solid matter which settles down during the primary and secondary stages of water treatment is called sludge. Common method used for settling out of impurities is sedimentation. This removal of large objects from influent sewage. Sedimentation. Most of the solids suspended in polluted water are too fine to screen out and too heavy to skim off. However, it can be removed by allowing them to settle down under the influence of gravity. This technique is called sedimentation. Sedimentation tank is generally shallow and radial-shaped. Polluted water is retained in the tank for a period of 3 to 4 hours. During this period, impurity settles down. Generally, depth of sedimentation tank is 3 to 5 meter and diameter is 30 meter. The tanks are equipped with mechanical arrangements like scrapper to remove sludge. At periodic interval, primary sedimentation tank removes 60 to 70% of suspended solids and 20 to 30% of BOD. Finely divided suspended solids colloidal particles cannot be removed efficiently by simple sedimentation. In such cases, sedimentation process is accelerated by mechanical flocculation and chemical coagulation. Mechanical flocculation. Here the wastewater is passed through a tank with the retention time of 30 meter. The tank is fitted with paddles rotating at a speed of 0.5 meter per second. Under this gentle stirring, the finely divided suspended solids comes together to form larger particles and settles down easily. Chemical coagulation. In this process, wastewater is treated with certain chemicals which are absorbed by suspended and colloidal particles present in water. The chemical coagulants commonly used in industry are hydrated lime, alum, ferric chloride and mixture of ferric sulfide and chloride. In addition, alum is the most popular chemical coagulant used for wastewater treatment, and coagulation is most effective and economical means for removing impurities. Neutralization. Highly acidic or alkaline water should be properly neutralized before it is discharged. Acidic water is neutralized by treatment with limestone or caustic soda depending on the type and quantity of waste present in the water. Alkaline water is neutralized by treatment with H2S04. When acidic and alkaline wastewater is produced in the same plant, then by mixing them in the appropriate proportion, neutralization is carried out economically. Equalization. Mining industries produce different types of waste having different characteristics at different interval of time. Due to this, uniform treatment is not possible. In order to solve such type of problems, wastewater coming from different units are retained in a big holding tank for a specified period of time. In this tank, wastewater coming from next unit is mixed thoroughly. A homogeneous mixture is formed. This mixture is then treated by normal sedimentation process. Secondary treatment. In this treatment, dissolved organic matter present in wastewater is removed by biological processes. The biological process involves bacteria and other microorganisms. The secondary treatment removes 70 to 80% of BOD. This method utilizes biological treatment processes. It removes dissolved colloidal and organic matter from wastewater. Microorganisms convert non-settlable solids to settleable solids. Bacteria and protozoa is used in this method frequently. Activated sludge. Process polluted water from sedimentation tank enters into aeration tank. Here 20 to 30% of active sludge mixed in the water. The mixture is aerated and mixed in the tank for 4 to 8 hours. The wastewater is then taken to secondary sedimentation tank, where the degradation and decomposition of all organic matter is carried out by microorganisms and bacteria. Some portion of the active sludge form during the process is circulated into the aeration tank for next cycle of treatment. Trickling filters or sprinkling filter. Organic material present in the wastewater is metabolized by the biomass. Organic substance grows in depth as the microbiotic matter preoccupied from the following wastewater is synthesized into new slime layer starts to grow sloughing. The composed fluid is conceded to a settling tank used for solid-liquid partition. Rotating biological contractor. This consists of a series of closely spaced plastic circular discs. Discs are submerged in wastewater and rotated slowly through it. Organic growths become close to the surfaces of the discs and form a slime layer over the whole wetted surface. The rotation of the discs contacts the biomass in the wastewater, then with the atmosphere for absorption of oxygen. Biomass utilizes the oxygen and macrobiotic substance for survival, thus decreasing the BOD in the wastewater. This treatment is used for removal of inorganic impurities at molecular level. Depend upon the nature of pollution on or move technique may be used. Following techniques are used for removal of impurities that remains even after 3 stages of purification. The chlorination. Gaseous chlorine or compound containing active chlorine such as bleaching powder par sodium hypochlorite is added to water. This compound generates hypochlorous acid, which acts as a purifying agent. Chlorination purifies water in 2 ways. It disinfects water from pathogenic bacteria. It controls the growth of undesirable algae in water. Coagulation sedimentation. Chemical coagulation sedimentation is used to increase the removal of solids from effluent after primary and secondary treatment. Solids heavier than water by gravity. With the accumulation of definite chemicals, solid masses can happen to be heavier than water and will straighten out. Adsorption. A physical process that is typically applied as tertiary treatment to remove low concentrations of contaminants from water that is difficult to remove by other means. Activated carbon has been processed to make it extremely porous, thereby creating a very large surface area available for adsorption to contaminants. Activated carbon may have a surface area as great 1,500 meters squared per gallon. Reverse osmosis. Osmosis refers to a process where pure water flows into a concentrated solution through a semi-permeable membrane. In this technique, impure water containing dissolved salt is placed above a semi-permeable membrane and subjected to high pressure. If the pressure is increased beyond value of osmotic pressure, water starts flowing in the reverse direction. Hence, this process is called reverse osmosis. The pure water flows down through the membrane and molecules in salt is retained by the membrane. Electrodialysis. This technique is used to purify water containing concentration of ionic impurities. Electrodialysis cell used for this process is divided into 3 compartments using two semi-permeable membranes. It is situated near the cathode, is coated with negatively charged ions. Therefore, this membrane repels the ions present in impure water but allows anions present in impure water to pass through it. When current is passed, cations get deposited in cathode, and anions on anoding central compartment carries water which is free from ionic impurities. Treatment technique in mines. Water gets polluted due to mining activity, hence for controlling water pollution following treatment techniques are adopted at mine, which includes treatment plant for mine discharge water, treatment plant effluent for workshop, treatment plant for discharge of domestic sewage. The pollutant water coming from mine is categorized into 3 classes. First, mine effluent. Mining activity are carried out below ground and subside water encounter is to be pumped out for facility this activity. This is major effluent involved in the mining operation. Therefore, to arrest suspended solid sedimentation tank are constructed and sediments are allowing to settle before being discharged. Workshop effluent. In big open cast mine workshop are constructed maintenance. Example HEMM. Major activity in workshop is washing and maintaining of vehicles. The effluent generated in workshop is treated in effluent treatment plant, which consists of pre-sedimentation tank, oil and grease trap, flash mixture, clariflocculator, clear water tank, etc. Domestic effluent. The life of coal mines is limited in the range of 10 years to 30 to 40 years. Duly constructed residential colonies have been provided in major mines. Most of these mines have been provided in major mines. Most of these mines have domestic effluent treatment plants, which ensures effluent quality within norms. Monitoring of effluent water is continuously done as per SPPAB guidelines and stipulations. In coal projects, it is very rare that any parameter exceeds the permissible limit. In fact, most parameters are below detectable limits. TSS in rainy season poses some difficulty and sometimes goes beyond limits. Workshop effluent treatment plant. In big, open-cast mines, workshops are constructed for maintenance of heavy earth-moving machineries. A major activity in the workshop is washing of the vehicles. The effluent generated in the workshop are treated in effluent treatment plant, which comprise of pre-sedimentation tanks, oils and grease traps, flash mixer, clariflocculator, clear water tank, etc. Domestic effluent treatment plant. The untreated discharge led to the serious environmental water pollution both to surface water and underground water table. The treatment is made through continuous aeration process on the principle of stabilizing decomposable organic matter in the sewage so as to produce effluent and sludge. The plant is designed for 0.5 million liter per day capacity of sewage input, having biochemical oxygen demand of 225 mg per liter and total suspended solids of 300 mg per liter, which after processing is reduced to 20 mg per liter and 30 mg per liter respectively. The following are the references of the study. That's all. Thank you for listening.